next thing I want to do is talk about binomial experiments. So the binomial distribution is a special kind of probability distribution, and it has to meet the following criteria. So first, we have to have a fixed number of trials. Our trials have to be independent, meaning they can't overlap. A good example of that would be heads or tails, right? Those events cannot both occur at the same time. Each trial must have all outcomes classified into two categories. For in that case, that's going to be success and failure. So for example, I successfully got heads, or I failed to get heads when I flipped a coin. And the probabilities also must remain constant for each trial. So here's some notation. So we have S for success, F for failure, N is the number of trials. Let X be the probability of the number of successes. Sorry, not the probability. X is just the number of successes. P is the probability of success, and Q is the probability of failure. Note that P of X, when I put that P out front, that automatically tells us we're looking for a probability. P of X is the probability of X successes. So let's go through an example. So one example of a binomial experiment would be to randomly select 15 M&M candies and determine if each piece were red or not red. So there's a fixed number of trials. There are 15 of them, right? And what we're doing is we're observing its color. Success would be red. Failure would be not red. Our trials are independent because M&Ms can only be one color. You cannot have an M&M that is both red and blue. Each trial can only have two outcomes because we're looking at red or not red. The probability of red remains constant at 0.20. Why is that? Okay, so how many colors of M&Ms are there? Oh gosh, now I'm putting myself on trial. So there's red, blue, brown, green, and orange in this case. Okay, I know we're missing yellow, but I honestly forgot yellow M&Ms exist. Okay, so here we have our 5 colors, right? And in this case, if we only have 5 different colors of M&Ms, the probability of getting red is 1 out of 5, so 0.20. Now for our notation. So S is if the selected M&M is red. Failure if the selected M&M is not red. So let's say I go ahead and pull 15. I get 3 red M&Ms. That gives me a probability of 0.20. And this, remember, this is the success. This is P of success. And this is the probability of failure. So success plus failure, the probabilities are always going to add up to 1. And probably P of 3 is what we want to find. There's a formula for this with a lot of moving parts, so let's take a look at it. You can also do this in Excel, so deep breaths. So how would you compute binomial probability? So the probability of X is n factorial over n minus x factorial times P to the number of successes, Q to the n minus the number of successes, where n is our sample size. So here I would have, let me go back. In our case, I'd have 15 factorial over 15 minus 3 factorial, 3 factorial times P cubed to the 15 minus 3. So I have 15 factorial over 12 factorial over 3 factorial times 0.20 cubed, 0.80 to the 12th. If I go through all that calculation, I get P of 3 is 0.25025. Now let's say you want to compute the probability of 5 successes in 8 trials if the probability of success is 0.30. What you want to do is use table A1. I have posted this to Blackboard, but it is also in your e-text and you can Google it. And it's the binomial probabilities table. It's pretty wide. So let's say you want to compute the probability of 5 successes in 8 trials if the probability of success is 0.30. You need to locate the n, looking down on the column to the far left, right? So here we have our probability distribution table A1. We need to locate our n, which is 8. So that's step 1. Next, what we need to do is we need to locate x. And x for this problem is 5, because we're looking for 5 successes in 8 trials. So let's look at our A1 table again. We now know the row we want. We want row 5. Cool. Next step, we need to locate the column with 0.03 at the top. So here's the table of 0.03. Let's go down. Okay, where 5 and 0.30 exist would be 0.047. So using this row from step 2 and the column from step 3, we see 0.04 is the 7. Now, let's go ahead and look at this table real quick and look at all the answers that are 0 plus mean. 0 plus. What does that mean? Well, 0 plus means the probability is very small. It's probably 0 to the first 3 decimal places, but the probability is still not exactly 0. It's just very, very, very close to 0. So again, this is our binomial table. It goes on to a lot more trials. It goes way above 8. You could have it at 15 and at 20. It's multiple pages long in the back of your book and on the PDF that I posted. So why don't you go ahead and try some, okay? So if you go ahead and look at what is the probability of 4 successes out of 11 if the trials of p equal 0.70, this is when you pause the video and go look in the table. If you do that, again, here's another one. What's the probability of 9 successes out of 12 trials if p equals 0.80? So go ahead, pause the video, I'm serious, and look these up in the trial. In the table. Okay, so welcome back. You should have gotten 0.017 and 0.236 as your probabilities. So let's talk about mean, variance, and standard deviation for the binomial distribution. So what's nice about this is our mean is just the number of trials by the probability of success. That's like so much easier to calculate than for other distributions, right? Our variance is n times the probability of success, probability of failure, and our standard deviation is the square root of that. So for our example, for this example, let's say we have the probability of a 7, landing on a 7 in roulette is 1/38. In experiment, the wheel is spun 100 times. So n is 100, the probability of success is 1/8. That means the probability of failure is 37 plus 38 because p plus q will always equal 1. Pinky promise. So to find the mean, I would take 100 times 1/38. That gives me 100 divided by 38 as my mean, which is 2.63. My standard deviation would be the square root of n times p times q, and for that I get 1.6.